Hello everyone. Let us continue the transient conduction heat transfer. In the previous lecture, we had studied about transient conduction, examples of transient conduction, different methods of solving transient conduction, and lumped system analysis. In lumped system analysis, we have studied that this system is applicable to those cases where the internal conduction resistance is very less compared to the convective resistance at the surface. This was stated qualitatively. Now, in this lecture, let us provide a parameter based on which we can check the applicability of lumped system analysis. For this, let us consider a steady state heat transfer in a plane wall. I'll consider the thickness of the slab as L. On the right side of the slab, we have a fluid with convective heat transfer coefficient H, and the temperature of the fluid is TA. On the left surface of the slab, the temperature is T1, and on the right surface of the slab, the temperature is T2. Let us assume T1 is greater than TA. The heat transfer occurs from left surface of the slab to the fluid. For this slab, Q conduction, which occurs within the solid, will be equal to Q convection, which occurs on the right side of the slab. Q conduction can be written as K into A divided by L into T1 minus T2, and Q convection can be written as H into A into T2 minus TA. When we equate these two and rearrange the equation, I can rearrange it as T1 minus T2 divided by T2 minus TA, that is the temperature difference or temperature drop in the solid to the temperature drop in the convection layer. That will be equal to L divided by Ka divided by 1 over Ha, which is equal to R conduction, that is the resistance offered for conduction within the solid body, divided by R convection, the resistance offered at the surface for convective heat transfer. And this can be simplified as H into L by K, which is equal to Biot number, Bi. Now I am introducing a dimensionless number called Biot number, which is named after French physicist Biot. Biot number is a measure of temperature drop in the solid relative to the temperature drop in the convective layer, that is T1 minus T2, that is the temperature drop in the solid, divided by the temperature drop in the convective layer, that is T2 minus TA. It is also interpreted as the ratio of conductive resistance in the solid to the convective resistance at its surface, that is R conduction divided by R convection. This ratio determines whether or not the temperature inside a body will vary significantly with respect to spatial coordinate. If the Biot number is less, then the variation of temperature within the solid body, that is T1 minus T2, will be smaller. So the temperature distribution within the solid will be uniform. So in this diagram, you can see that we have plotted temperature profile for three cases: when Biot number is very much lesser than 1, when Biot number is equal to 1, and when Biot number is greater than 1. In the case when Biot number is very much lesser than 1, the temperature difference across the slab or the temperature drop across the solid is very small, and this can be considered as a uniform temperature within the solid. But in the case of Biot number equal to 1 as well as greater than 1, the temperature profiles are not uniform and they are varying linearly inside the solid. Now let us consider the case for transient conduction. In the first diagram, it shows a slab, and this is the case temperature distribution for Biot number less than 1. In this, we can see that the temperature gradient in the solid is small and can be taken as a function of time only. The second diagram shows the variation of temperature within the body when Biot number is equal to 1. the temperature drop across the solid is comparable in this case. The last diagram shows the temperature distribution when the Barth number is very much greater than 1. The temperature drop across the solid is much larger than that across the convective layer at the surface. Therefore, to fix the criteria for which lump system is applicable, let us define Barth number in general form as follows. Barth number, that is Bi, is equal to H into Lc by K, where H is the convective heat transfer coefficient at the surface, K is the thermal conductivity of the solid, and Lc is the characteristic length, which is defined as the ratio of volume of the body to its surface area. Lc is equal to V by A. With these definitions of Barth number and characteristic length for a simple geometric solids like slab, cylinder, and sphere, it is found that transient temperature distribution within the body will be uniform, with the error being less than about 5% if Barth number is less than 0.1. In other words, if the conduction resistance of the body is less than 10% of the convective resistance at the surface, the temperature distribution within the body will be uniform within an error of 5% during transient conduction. So this is the criteria which has to be looked into when we are deciding whether lump system analysis can be applied for a geometry or for a given problem or not. When using the characteristic length, it is defined based on the geometry of the object. So here we have a characteristic length for common shapes. First one is the plane wall. I'll consider the thickness as 2L. Characteristic length as it is defined is volume of the object divided by the surface area. In the case of plane wall, the volume is area multiplied by 2 times of length, and the surface area, since we have two surfaces, it is 2A. So when we simplify this, we will get characteristic length as L, which is equal to half thickness of wall. The second one, long cylinder with radius capital R. Characteristic length is equal to volume by area. For a cylinder, volume is given by cross-sectional area, that is pi r square into length L, and the surface area is given by 2 pi RL, so which is equal to R by 2. Third one, a sphere with radius R. Characteristic length is equal to volume by area, where the volume of the sphere is given by 4 by 3 pi r cube, and the surface area of the sphere is given by 4 pi r square. So the characteristic length is R by 3. And for cube side with side L, characteristic length is given by volume by area, and the volume of cube is L cube, and the surface area of the cube is 6 times of L square. So the characteristic length in this case will be L by 6. With this definition of characteristic length for common shapes, we can write theta by theta I, which is also equal to T tau minus Ta divided by Ti minus Ta, is equal to e to the power of minus tau by T, where tau is the time and T is the thermal time constant if Barth number is less than 0.1. With this lump system analysis, let us solve few problems. Problem number 1. A 15 mm diameter mild steel sphere K equals 45 watt per meter degree Celsius is exposed to cooling airflow at 20 degrees Celsius, resulting in a convective coefficient of H equals 120 watt per meter square degree Celsius. Determine the following. A. Time required to cool the sphere from 550 degrees Celsius to 90 degrees Celsius. B. Instantaneous heat transfer rate 2 minutes after the start of cooling. For mild steel, rho equals 7850 kg per meter cube, Cp equals 475 joule per kg degree Celsius, and alpha equals 0.045 meter square per hour. First, let us list out the data. The geometry is sphere, diameter d equals 15 millimeter, K 42 watt per meter degree Celsius, surrounding fluid temperature TA is 20 degrees Celsius, convective heat transfer coefficient H equals 120 watt per meter square degree Celsius, then density rho equals 7850 kg per meter cube, Cp equals 475 joule per kg Kelvin, and alpha equals 0.045 meter square per hour. We need to find out the time required to cool the sphere from 550 degrees Celsius to 90 degrees Celsius and the instantaneous heat transfer rate after 2 minutes after the start of cooling. The first thing which we have to do while solving any transient conduction problem is that we need to find out the Biot number to decide whether lump system analysis can be applied or not. So let us find out the Biot number. Biot number is given by H into Lc by K, and for sphere characteristic length is R by 3. Therefore Biot number is given by H into R by 3 into K, which is equal to 120 into 15 into 10 to the power of minus 3 divided by 3 into 42 into 2. So the Biot number is 0.0071, which is lesser than 0.1. Since the Biot number is less than 0.1, lump system analysis is applicable. We know that for lump system analysis we have T tau minus Ta divided by Ti minus Ta is equal to e to the power of minus tau by T, where T is the thermal time constant given by rho Cp divided by H into A. V by A can be written as Lc, so I can write T as rho Cp Lc by H. So when we substitute the value of density, specific heat Lc and heat transfer convective heat transfer coefficient, we get time constant as 77.68 seconds. Now let us calculate the time required to cool the sphere from 550 degrees Celsius to 90 degrees Celsius. Here I know the initial temperature Ti as 550 degrees Celsius and the final temperature T tau as 90 degrees Celsius. Now if I substitute these things in the above equation, 90 minus 20 divided by 550 minus 20 will be equal to e to the power of minus tau divided by 77.68. So tau will be equal to 157.26 seconds. Now we need to find out the instantaneous heat transfer rate 2 minutes after the start of cooling. For that, the instantaneous heat transfer equation is Q tau is equal to H into A into T tau minus Ta. First we need to calculate T tau to find out the instantaneous heat transfer rate. In this case, we need to find out the instantaneous heat transfer rate after 2 minutes, so tau can be taken as 120 seconds. Now I'll substitute all the values in the equation T tau minus Ta divided by Ti minus Ta is equal to e to the power of minus tau by T. From that I'll get T tau as 133.1 degrees Celsius. And we need area, so area for a sphere, surface area of a sphere is 4 pi r square. By substituting that I'll get the area 7.07 into 10 to the power of minus 4 meter square. When I substitute these values in instantaneous heat transfer equation, I'll get the instantaneous heat transfer rate as 9.6 watts. Now let us go to the next problem. A thermocouple junction, which may be approximated as a sphere, is to be used for temperature measurement in a gas stream. The convective coefficient between the junction surface and the gas is 400 watt per meter square Kelvin, and the junction thermophysical properties are K equals 20 watt per meter Kelvin, Cp equals 400 joule per kg Kelvin, rho equals 8500 kg per meter cube. Determine the junction diameter needed for the thermocouple to have a time constant of 1 second. If the junction is at 25 degrees Celsius and is placed in a gas stream that is at 200 degrees Celsius, how long will it take for the junction to reach 199 degrees Celsius? In this case, we have a thermocouple which can be approximated as a sphere, and the thermophysical properties of the material is given. First, we need to determine the junction diameter, so that the junction has a time constant of 1 second, that is the thermal time constant, and then it is placed in a gas stream which is at 200 degrees Celsius. We need to find out the time required for the junction, which is at 25 degrees Celsius, to reach 199 degrees Celsius after placing it in the gas stream. First, list out the data. The geometry is sphere. H is equal to 400 watt per meter square Kelvin. K equals 20 watt per meter Kelvin. Cp equals 400 joule per kg Kelvin, and rho equals 8500 kg per meter cube. Now we need to determine the diameter if thermal time constant is 1 second, and the time required if the initial temperature is 25, T tau is 199, and Ta is 200 degrees Celsius. Again, whenever we are solving transient conduction problems, first we need to find out the Biot number, which is given by H into Lc by K, and for a sphere Lc is R by 3. In this problem, we don't know the radius, we need to find out the radius. So what I will do is, with the help of the thermal time constant, which is given as 1 second, I will find out the characteristic length. From that we will be able to find out the diameter, and later we will substitute that in the Biot number equation and find out whether the Biot number is less than 0.1 or not. If it is less than 0.1, our approach is correct and the diameter holds good. Otherwise, we need to change our approach. So I'll take T, which is equal to rho Cp into V by H into A, or V by A can be written as Lc. So I'll substitute the values. Time constant is 1 second. So 1 will be equal to 8500 into 400 into Lc divided by 400. So I'll get the characteristic length Lc as 1.18 into 10 to the power of minus 4, and for a sphere it is R by 3. So the radius will be 3 times of 1.18 into 10 to the power of minus 4, that is 3.53 into 10 to the power of minus 4 meters. So the diameter will be 2 times of the radius, that is 2 into 3.53 into 10 to the power of minus 4. So D will be equal to 7.06 into 10 to the power of minus 4, or 0.706 millimeter. Now I will substitute the characteristic length or the diameter or the radius in Biot number equation, and let us see if the Biot number is less than 0.1. So if I substitute the characteristic length in Biot number equation, I'll get the Biot number as 0.00235, which is less than 1. Since the Biot number is less than 0.1, lump system is applicable and the procedure used to calculate the diameter is valid. We can proceed and find out the time required to reach 199 degrees Celsius. So for that lump system, T tau minus Ta divided by Ti minus Ta is equal to e to the power of minus tau by T. Now we need to find out tau. So I'll substitute the remaining parameters and I'll get the time as 5.16 seconds, which means to say that we're using this thermometer. If we want to measure the temperature of a gas stream which is at 200 degrees Celsius, then we have to wait for a time period of 5.16 seconds before we will be able to accurately measure the temperature. We'll go to the next problem. A 12 mm diameter MS sphere at 540 degrees Celsius is exposed to cooling airflow at 27 degrees Celsius and heat transfer coefficient of 114 watt per meter square Kelvin. Find A, the time required to cool the sphere from 540 degrees Celsius to 90 degrees Celsius. B, instantaneous heat transfer rate 2 minutes after the start of cooling. And C, total heat transfer from the sphere during first 2 minutes. Properties of MS are: rho equals 7850 kg per meter cube. C is 475 joule per kg Kelvin. C is nothing but specific heat Cp, and alpha is equal to 0.045 meter square per hour. And now let us list out the data. The geometry is sphere. Then initial temperature is given as 540 degrees Celsius, fluid temperature is 27 degrees Celsius, heat transfer coefficient is 114 watt per meter square Kelvin, then the density is 7850 kg per meter cube, and specific heat is 475 joule per kg Kelvin, and the diameter is 12 millimeter and alpha is 0.045 meter square per hour. Now we need to find out tau. If T tau is 90 degrees Celsius, then we need to find out instantaneous heat transfer at Q tau if tau equals 2 minutes, and we need to find out Q total for first 2 minutes. In all transient conduction problems, first we need to find out the Biot number. So let us find out the Biot number. Biot number is given by H into Lc by K, and this is a sphere, so Lc will be R by 3. And in this problem they haven't given us the thermal conductivity of the material, but they have given alpha. We know that alpha is equal to K by rho Cp. From that, K or thermal conductivity will be equal to alpha into rho into Cp. Here alpha is given as 0.045 meter square per hour. It is given in terms of hour, which needs to be converted into meter square per second. So that is done by dividing alpha by 3600. So K will be equal to 0.045 divided by 3600 into 7850 into 7475, which will be equal to 46.609 watt per meter Kelvin. Now I'll substitute this in the Biot number equation, and we will get a Biot number of 0.004892, which is less than 0.1. Since Biot number is less than 0.1, lump system analysis is applicable in this case. Now let us find out the time required to reach 90 degrees Celsius. For lump system, T tau minus Ta divided by Ti minus Ta will be equal to e to the power of minus tau by T, where T is given by rho Cp V by H into A or rho Cp Lc by H. When I substitute the values, I'll get the time constant as 65.41 seconds. Now I will substitute these values in the lump system analysis equation to get the time. So when I substitute that and simplify, I'll get the time as 336.34 seconds. So it requires 336.34 seconds to reach 90 degrees Celsius if the initial temperature is 540 degrees Celsius. Now I need to find out the instantaneous heat transfer rate 2 minutes after the start of cooling. For this, the equation is H into A into T tau minus Ta. We need to find out the surface area, which is given by 4 pi r square for a sphere, and that will be equal to 4.52 into 10 to the power of minus 4 meter square. And then we need to find out T tau after 2 minutes. So tau will be 120 seconds. I'll use T tau minus Ta divided by Ti minus Ta is equal to e to the power of minus tau by T, and I'll substitute all the values except T tau, and I'll get a value of T tau as 108.93 degrees Celsius. Now I'll substitute the value of area as well as T tau in the above equation. I'll get Q tau as 4.23 watts. Now I need to find out the total heat transferred from the sphere during the first 2 minutes. So for that, equation is Q total is equal to mCp into T tau minus Ti till tau equals 2 minutes. Again for this I need T tau and I need mass of the sphere. So mass is given by rho into V, that is density into volume, and for a sphere volume is 4 by 3 pi r cube. So when I substitute the values, I'll get the mass as 0.007103 kg or 0.7103 grams. I'll substitute the mass and the T tau, which I calculated in the previous step, and I'll get the total heat transfer rate as minus 1454.29 joules. Here we have a negative sign which indicates that the sphere is losing heat or we are cooling the sphere. I think this will help you in understanding the criteria for lump system analysis and the method of solving problems using lump system analysis. In the next class, we will talk about the graphical method of solving transient conduction problems when the Biot number is greater than 0.1. Thank you.